Good evening, everybody. This is Obi-Wan Pez for Simplex Pachinko. We are back to cracking the GRE math test from 2002. I will say, right, probably not much has changed, generally speaking. There might be some nuances that are a bit different, but at the same time, overall, it's going to be more or less the same test, right? We got to check your mathematical knowledge in all of the different areas and see how you measure up to make sure that you have a bachelor's level of understanding for mathematics. And GRE being, you know, your I don't even remember what it stands. Graduate requisite exam, something like that. Does it even say? Cool. I think this one actually came with a CD in the front of it. I don't have it, so it must not be that important. I'm slightly surprised that it didn't have like a really quick blurb at the front. Oh, there we go. Graduate record examinations. Yep. All right. So, have to make sure that you have a bachelor's level of understanding of mathematics before you can move on to graduate level. And the GRE math exam is going to require a different kind of score depending on what level or what subject you're going into for graduate school. Mine being, you know, intending on going to math education or math education, mine had to be pretty decent. I don't even remember what I got. It's probably on the ETS website somewhere, I'm sure. I probably put it on one of my first resumes. Okay, so we ended off with looking at find a formula for F inverse and then show that it works for all real x values that we can plug in, and also, right, we had to worry about what happens when F inverse at 0 is 0. So in this particular case, we had to unrationalize the denominator in order to ensure that it no longer had the discontinuous nature at x equals 0. Hey Zach, happy Wedge Day. It is, I mean, it is still Wednesday technically. GED? Yeah, GRE. Gotcha. Nah, that's all right. My instructor from really? Uh-oh. I think okay, there we go. Got me worried a sec. the stylus was not responding. So every so often that happens, you just got to hit escape a bunch of times. I'm really glad it's an easy fix. Yeah, my instructor for Eskrima and Tai Chi sent a text message at like 10:30 in the morning, and since my phone was like doing something else, the notification came and then went, and then I didn't go to the home screen because I was doing other stuff the whole day. So there was a nice little notification that said, hey, we're gonna start we're doing a like Tai Chi group. If you said you were interested in doing this, I don't know if you're back in the country yet because I was up in Scotland. Country. But we're gonna start at like 1:15. I got this message at 1:45. Finally, actually looked. It's like, yeah, great. That's. I wish it had said something in my ear or like made a bigger deal than just kind of. But what can you do? Cool. So, looking at the remainder of the GRE Precalculus stuff, we have a section on graphs in the XY plane, and then we move on to analytic geometry. So, analytic geometry is, in short, the conic sections. So, deals with deals with all of the conic section stuff that some precalculus classes have covered and others have not. So this is always an interesting one to discuss. Our precalculus course did not cover conic sections, and my original department chair wanted me specifically to start teaching conic sections as like a bonus material thing for the honors like breakout session. 1 hour a week. We just go and chat about conic sections for like an hour, or 50 minutes. And I went through probably about 3/4 of the material, and I was like, you know what, I don't really like this too much. Who wants to just chat about like math history? And everybody said yes, please. So I went to my department chair. I was like, okay, so here's the thing. Really love the idea about conic sections, but I'm not good at it, and the students are much more interested in math history. And she was just like, well, I think you missed the point, but yeah, okay. And so I taught math history for like a good 10 years as a bonus class. And when I wasn't teaching it as part of the honors breakout session, I was oftentimes just teaching it in class anyway as we went through stuff. And sometimes the students from my class would come in and be like, yeah, you taught us this. I was like, great, but the other half of you don't know what I'm talking about, so let's just real quick at least go over it. Most of the time they were happy enough to hear it a second or third time. I do like telling my stories. Old man Obi is in effect. Okay. So sketch the graph of the following function. F of x is equal to, we have a piecewise function, square root of 1 minus x squared, where x is going to go from -1 to 0, including first, excluding second, and absolute value x minus 1, where x is going from inclusive 0 to infinity. Now it is perfectly fine, whichever one is open or closed, or can be just about anything, but you can never have overlap between the two of these. So if this was also closed, in order for this to be a function, both of those values would have to be the same. So plugging in a 0 into each part would have to give us the same number. As it turns out, it does. So this is going to be a continuous function, and we can talk more about continuity a bit later. Anybody who's taken Precalculus probably has the understanding that, you're putting parts of a graph together, and if you can draw it without lifting your pencil, at least, and not overlapping any particular y values, then it's going to count as continuous. And yeah, okay, fine enough. Right, so f at 0 for both of these cases ends up being 1. So because it's the same, then we could in fact have both of these zeros as closed values. It's poor form to do that. It's bad habit to get into, but it's not completely wrong. At least, again, in the case where they are identical. If they are not identical, so if this was 4 minus x squared, and we plug in 0 to both of these, we get up top, square root of 4 is going to be 2, and at the bottom is still going to be 1. So if we get a 2 and a 1, now it's just wrong. If they're not the same identical values, then it's wrong. If they are identical, then it's poor form, but it's not wrong. This kind of extends from what we talked about before when we were talking about absolute value functions. The absolute value of x is equal to, it's a piecewise function. It's going to just be x if x is greater than 0. It's going to be the opposite of x if x is less than 0. And then one of these has to include 0 itself. Because we want this to be a continuous function, we want it to include all possible x values, and there's no problem with just having the absolute value of x, or absolute value of 0. That's perfectly fine. So it doesn't matter whether you put it on this one or you put it on this one. Again, putting it on both is poor form, but you get identical values. So again, it's not wrong. It's just poor form. For the most part, I put it on the positive one just 'cause. It's just a reminder. And we'll go like this. Okay. Okay. So for this particular function, what we're going to do is we're going to say we want to graph each of these pieces. Let's use straight lines, actually. Close. Okay. Just looking at this stuff, the outputs of both of these are going to be positive numbers. So that's also something to recognize when you are doing pre-calc, when you're doing function analysis. Right? Know what kinds of functions you have, what their standard inputs and outputs are going to be, and how they get transformed by doing all sorts of stuff like this. So up top, right, we have a square root function. Square root function will input stuff that is positive, or rather non-negative, and then it will output only things that are also non-negative. The bottom stuff here, absolute value, if we just have a standard absolute value function, again, that's this stuff here, that is going to be inputting any value you want and outputting only non-negative values again. So, right, non-negative values that are all coming out. So we can do any sort of, or we can line up our axes so we only have positive and 0 coming back. I know from experience that this is going to be a circle, or at least part of a circle. Reason being for that, oh right, we also need to get rid of the 4 part there. That was just a 1 minus x squared. Right, so how do you maybe work with that? Well, if you were to say, well, this is y equals the square root of 1 minus x squared, then in order to expand this out, you can square both sides. You make it y squared is equal to 1 minus x squared, and then move the negative and make it x squared plus y squared is equal to 1, right? Now again, I know that as an experienced mathematician that yes, this is the equation of a circle from the most basic form. Very appropriate that we're also going to be doing conic sections a bit later because a circle is one of the conic sections. So with this, we can also say then, okay, this is at least part of a circle, the top part, because all of our values are going to be positive, and our x values, our domain values, are going to be from -1 to 0. So that's only half of the upper part of the circle, or in other words, 1 quadrant only. So we end up getting something that goes, yeah, it's fine. Right, from -1 to an x value of 1 here. Close enough. Again, if we're just like drawing, then, oh, right, and not at 0. So this is going to end here. Starts from -1, 0. If you need to worry about what those values are, go and plug them in, try and figure out what they're going to be. Again, since this is a square root function, we're only going to get positive numbers back, and we have to plug in numbers such that the inside is non-negative. So where is it 0? It's 0 at 1 and -1. When you square it, you subtract it from 1, you end up getting 0. If you choose any values which are larger than 1 in either the positive or negative direction, then we end up getting big numbers that are being subtracted from 1. So 1 minus 5 is going to be 4, sorry, -4. But then we get imaginary numbers. We don't want that. So the context for this particular problem is that this is going to be only within the boundary from -1 to +1 on the x values, and from 0 to 1 in the y's. But then, again, we have another notification here that we are only going from -1 to 0, not all the way to +1. So then what does that mean? Okay, from here we say we want the absolute value of x minus 1. This is then going to start at 0 and go off to infinity. So from here, what do we get when we plug in 0? Again, this is going to be 0 minus 1 is -1. Take the absolute value, that's +1. So now we're at 0, 1. It overlaps with the quarter circle. at this exact point. Then this has a slope of either positive or negative 1, just as was talked about here. And then where does it change direction? Well, if you know function transformation, you know that this absolute value function has been shifted to the right one place. And it's a V shape that has its vertex at that particular point 1, 0. All right, if you don't know function transformation, plug in numbers. So what do we get? 1 at x equals 1. 1 minus 1 is 0. Absolute value is 0. So now we get the point 1, 0. At 2, it's going to be 2 minus 1 is 1. Absolute value of any of those numbers are still going to be positive. So they don't change. So 2 minus 1, we get 1 again. So now we're going to be at 2, 1 as the next point. Right, and then our absolute value just goes off that way. Okay, so then what happens? Well, this is going to continue on forever because we have this notification here that our domain is going to start at 0 for the absolute value section of this function and then go off to infinity. Whereas the square root function is going to start from -1 and stop at 0, or stop approximately at 0. Right, so this is going to be our first one. If anybody has any questions, let me know in chat. If you're watching this on the video on demand, welcome. Thank you for coming. We also have YouTube channels for anybody who is live. We have gaming content at Obi-Wan-Pez, and we have mathematics content. This is where you're watching it if you are on YouTube, at nsimplexpachinko6542. Still can't do anything about the numbers yet. Next one. We can't actually, hang on. To be fair, right? We do know real easily. I could just glance at it and know exactly where I'm going to be graphing this. But to be fair, we're going to sketch the following. This is, let's just change it up and make it a G just because. 2 minus x squared, where x is going from -2 to +1, inclusive on both. And, oh, that's cute. So there are multiple ways to do this particular one. The proper notation generally looks something like this. Okay, now what on earth is that? If you've never seen this before, this could really throw you off. So, it has multiple names. This will generally be known as greatest integer function. GIF before you ask. Which has alternate forms. In MATLAB, well, maybe not MATLAB, but in most programming languages, it is int of x because you're looking for the greatest integer. Actually, in MATLAB, it is floor. Because you're looking at where is the floor for this particular number. If you were looking at, like, you know, a height of an elevator, right? What floor is it resting on? If you're looking at that particular wording, then the British system is, or really anywhere in Europe, is much more favored because they start numbering floors on ground, which is sometimes, and I was very happy to see this in Bath, is sometimes known as the 0th floor. Because what happens when you go up from 0? You hit the 1st floor, which is a little bit of an adjustment for an American, but still, 2nd floor, 3rd floor, etc. What happens when you go down? You do not go from 1 to basement, or from 1 to -1. You go from 0 to -1, and it makes sense. Now, I will grant you, right, the 1st floor is going to be the 1st floor that you stand on. So it makes sense from, you know, that particular perspective. But nonetheless, these days, I think it would be beneficial if the Americans switch over to the same system the rest of the world is using. Shocker. All right, floor function also sometimes looks like this. These are not L's or backwards L's. These are little bits that go like that in order to say we want the floor function. Yeah, I mean, pretty much all mathematicians and physicists want the metric system. We use it anyway. I'll tell you what, the change will happen. You watch, somebody will be put in office somewhere, and they will make it. Here's what I want. They will follow the plan. They will follow through on the plan we should have just done, which is you take like 2 to 5 years and you say, okay, look, at the end of this period, whatever it is, both things need to be on there. At the end of another 2 to 5 years, they must switch places so that the metric is always above the imperial. Another 2 to 5 years, the imperial must be smaller. Like half the size. And eventually it's just going to be like, whatever. Most places put both on there anyway. So it's like, just put the metric one higher and then make it bigger. Or make the imperial smaller. So yeah, int, floor, or floor symbol. Either any of those work. We also have the least integer function. Correct me if it's called anything slightly different. I mean, I know the one word we're looking for here, but we typically call it the ceiling function. So in MATLAB, it will be known as CL of x. I'm kind of curious now if that's true in Scilab, which is French, which makes perfect sense. Wait, what? Ceiling is greatest integer? Yeah, okay. Right, the greatest integer that is less. And ceiling is least integer, which is greater. It's always great when the math teachers start worrying about notation. Keep in mind, right, we're all human. We're still making mistakes. It's all good. And now the ceiling function looks like this. So it's got the tabs at the top, and then it's pointing down like that, because we want to know where the ceiling is. So just like, again, you know, which ceiling is this? Depending on the height. So you're looking at what is the, or like what's the next floor up, basically, is what you're looking at. It's the same as the ceiling. The ceiling of this floor is arguably the same as the floor of the next floor up. Actual engineering notwithstanding. Okay, so here we're going to do the same sort of thing. We do want to know where is this going to be, approximately. So we'll drop this here for now, and then go bloop and decide where we're going. So 2 minus x squared, from the value -2, we plug -2 in, we end up getting a 4, right? -2 squared is going to be 4. And then 2 minus 4 is going to be -2. And then we have a 1, which is going to get us 2 minus 1 squared is 1, so it's a 1. So we go from -2 up to +1. And the greatest integer function is going to be looking at what is the floor that we have. No matter what number we pick, what is the next integer downward from wherever we are? Unless you're at an integer, in which case it's just where you are. Again, what is the greatest integer that is less than... I misspoke. Say, what is the greatest integer that is less than or equal to your current location? Okay, so we're going to go like this and go 1, 2, 3. And downward. We only need to get to 2, really. These are not very well spaced, but you know what, it's fine. We are doing this as an approximation. It's not super, super important that everything is perfect. Alright, we'll do this and say that that's -2, -1, 2, 1. It's a little better. Actually, where I wrote the actual number is pretty good. Okay, so what we're going to do here is we say that our first one is a parabola. It is a standard y equals x squared parabola. It has been transformed, not in shape, but in its location. So first thing that we're going to look at is this is an upside down U shape because our A value is negative. Since the A value is -1, the only thing that's happened is that instead of being a parabola up, it is now a parabola down. Can't quite get that. Jeez, awkward. Anyway. Then the 2 in front of it is going to be adding 2 on the outside of the function. So that is going to shift everything up 2 positions, up 2 spaces. So here we're going to have our vertex at 0, 2. Again, if you want to, you could just plug stuff in and see what happens. This is always going to be 2 minus x squared is always going to be a positive number. And it doesn't matter whether it's the positive version or the negative version of that particular number. It's always then going to be squared, become positive, and get subtracted from 2. So here this is going to always end up being less than 2 everywhere else. If x is 0, then we get the maximum possible value of 2. Okay, so now we see that at 1 or negative 1, we end up with 2 minus 1, which is 1. So 1, 1, and negative 1, 1. And then we had negative 2 was going to get us negative 2. Keeping in mind this is a U curve, and it starts from x equals negative 2, and then goes to x equals 1. We're going to get, again, parabolic. It's going to start very slowly and then start accelerating as it goes out further and further. And then we do the same in the opposite direction. Try and make it symmetric as best as we can. Okay. Now what? Well, we've got this greatest integer function, which is at the value of 1, it attains the value of 1. Right? We want the greatest integer, which is less than or equal to the current value, whatever it might be. So at 1, this function attains the value of 1. Unfortunately, somewhat, it's already got a value here. We don't have to, or x being 1 is not included in the greatest integer function. However, at 1.000, as many zeros as you want to put in 1, it has to be a finite number, this is now going to keep this same value of 1. It's not going to change. We could even go all the way out to 1.5. And this says that the greatest integer that is less than or equal to our value of 1.5 is going to be 1. So it stays at 1. It's going to continue staying at 1 until we get to 2. At 2 exactly, the value attains an output value, or the function attains an output value of 2. And then from there, that's going to hold the output value of 2 until we get to 3, etc. At 2 itself, it is not going to be at this location, so we put an open circle here, and then it jumps up to the closed circle above. This is approximately what you would see in an elevator, like light system to tell you what floor you're on. Back in the old days, it used to be just a slider that went back and forth, and then you could tell which floor it was on, or you'd have the little dial system. Those worked fine. Right, this is going to continue doing its thing forever now, because again, we're going out to infinity. But you know, I hesitate to put like an arrow here, because it's not going to stay at this value. It's going to continue this pattern, which is going to continue going up every time we reach a new integer. So I often just put an ellipsis at the end to say like this, just going to keep doing what it's doing. Right. That's it for this. Again, any questions, let me know. Okay. So for analytic geometry, generally speaking, we talked about this before, this is what are called conic sections. We've seen conic sections before in pretty much our entire lives. Every aspect has some sort of, conic section that is in it somewhere, whether or not we know it. That's not to say literally everything is conic sections, but they exist in many, many different places. So first off, if we're going to have conic sections, we got to discuss a cone. So if we look at cones just as they are, right, we have, this could be done a number of different ways. So one is that we take a circle and you chop out some section of it. So cut until you reach the center. And then do that from two different places. You end up making a little wedge which comes out. Then, when you bring the two pieces together, you tape those two sides together, and it ends up forming a seam, and the paper will pop up out of the second dimension and into the third. Reason that it does that is similar to, you've probably seen other similar examples before. If you have too little material to make a flat object and you try to connect pieces of it together, oftentimes it will create something that is curved into the third dimension. Now this one is a bit pointy, but nonetheless, it's it's coming off the table and no longer able to remain in the second dimension. If we want to, again, close that gap. So if you just do this with, make a circle on a piece of paper or print one out, cut it out, and then, again, chop out a wedge. Find the center of that circle. Pretty simple if you end up, just take the circle and fold it in half in a couple of places, and you'll figure out where the center is real quick. Right, if it's a true circle. So anyway, we end up with this cone. All right, cool. So what happens if we want to take a plane all right, take a plane, take a piece of paper, and take a playing card with a bit of clay, and lop that thing directly through the cone. You might need to use a knife or something. Be very careful how you do this. But, right, if we were to take that plane and run it directly through the cone, what would we end up getting? Well, that would end up chopping out a circle. How do we know it would be a circle? Well, guess what the base is? Right? It's a circle sitting on the ground. sitting on a different plane. But if we just take any sort of slice of this cone exactly horizontally, then our right cone is going to now have a slice taken out of it, which makes a smaller right cone on the top, and then a circle for the bottom. Again, if you take a piece of clay, I have clay. Do I want to make a mess? Not really. Well, not quite, Seth, so we're getting to that. Right? If you take that plane and you slightly make it off angle. Right, so we make this tilted plane and we run it through the cone. It's not like tilted a lot, but it's tilted some. Then we're still going to get like these individual points, which you can see on the edges here and here. Notice where they are, right? These are no longer on the same horizontal plane. These are now tilted like this. And you're probably saying, well, yeah, that was what you said a minute ago. Well, what does that do for us? Keep in mind, like, this is probably just a fault of how I drew it, but nonetheless, the center line of the cone should be here, and this doesn't really appear to be the center anymore of this tilted thing. Because up higher, it has a smaller distance to the center, and down lower, it has a longer distance to the center. And I don't think that that is wrong if you look at it along the tilted line either, right? It should just make sense. By visual inspection, yes, that seems to be true. But I don't want to speak for every possible example, right? This is still tilted. Yeah, it makes sense. Maybe we could prove it later. But either way, so this is going to come out, and then it's going to go this whole distance, and then it's going to swing back in. Right? Our center should be like here. Right? So now it looks kind of like a circle, but not quite. And in fact, in this particular case, it is no longer a circle. It is going to be stretched in that tilted direction. And the longer that we make, the more tilted that we make this, the more extreme the case is going to be. The more that center is going to move down toward the end. Yes, right. And the width of the cone is still going to remain approximately the same, but then the depth of that cone that we're cutting, the shape that we're making here, keeps getting stretched further and further and further out as that keeps going, as this side keeps going down. Well, not that way, right? As this slides down the cone further and further. The distance keeps increasing more and more and more. So this is no longer a circle. Right, this is actually going to be an ellipse. Now, I will say, just like just like a square is a special rectangle, right? So too a circle is a special ellipse. Thank you, Maxie. Fine. Gotta keep me honest. Alright, so as that keeps increasing further and further and further, right, our shape becomes more and more extreme, and it becomes, we'll talk more about the actual word for it. Oh, gotcha. So I don't know if it is excluded within the definition. Because then you could do the same for all of these things in the exact same way. Asterisk. So I think if you... yeah. So like a point is a conic section, but the problem is that like an ellipse, I think by definition an ellipse should have a non-zero value, just like all the rest of them. Should have a non-zero value in at least one of its coefficients. So a point ends up just being, you know, like a single location where this works. Where x has to equal something and y has to equal something, and that's it. So, oh, come on. Again, easy fix. But wish it didn't happen at all. Okay. So now, the next question becomes, so what happens when I cut the plane exactly parallel to the opposite side? Right, what happens when I cut the plane exactly parallel to the opposite side? Oops. So this plane is just going to keep going on forever. It is an infinite plane, so it's just going to keep going on forever in every direction. But what happens here? Well, we end up getting this point which cuts in. That's the first initial point when we cut into the cone, and then from there we're going to get this still, like, you know, spreading out horizontally, but then we're going to be moving faster and faster in the diagonal direction. I say horizontal, it really means nothing from that particular point of view, but this is going to go down like this. It's going to come out as it keeps going, and then it's just going to keep going outward. And in this case, because it's parallel to the opposite side, it's never going to reach the opposite side of the cone and then like terminate like an ellipse or like a circle. It's just going to keep going forever and ever and ever. So now this should also look rather familiar. So this is a parabola. Alright, do you shift up the plane a bit? Do you get a point? Alright, so yeah. The point, just moving that up, you do get the point is a conic section. So I wasn't really specific about that. Sorry. And the other thing you can do is just literally take the plane and lie it along the edge. Just let it sit on the edge. And in that case, we have a line. Ellipses all the way down, yeah. Almost. Alright. So, what we're looking at is... We're not done yet, there's one more. But, with what we have here, right? We have a single point, a line, if you put it along the edge of the cone. We have circles if you just cut it straight across. You've got ellipses if you cut it at a diagonal. And parabolas if you cut it at a parallel parallel slope to the opposite side. So technically, yes. However, part of the, part of the drawing of the picture of making conic sections is ensuring that you have a double pyramid, a double cone. Reason being, that all of the other stuff that I've said so far, all the stuff that we've created so far, is all true, with the exception of, again, it would be technically a ray coming from a point and then going in one direction. In this case, we can create this by making a double cone, one that also goes up. And in so doing, we can also create the fifth, 6th type of conic section, where we take this and we say, okay, now don't just do the parabola where it's parallel, but go further than that and cut your plane this way. We're going to adds, so we'll be right back. Sorry. Dun dun dun.
Then I was floating down a river of plump white pillows, through a forest of fluffy cushions, under a crystal pendant sky.
So that's the dream you had?
Yep.
And how you want to decorate the bedroom?
Yeah.
Right then, Wayfair it is.
With furniture and decor for every style and budget, Wayfair can turn your home dreams into reality.
Did I mention the light-up inflatable chair?
Get it out of your head and into your home with wayfair.co.uk.
We don't have enough staff to clean a whole office block, I'm afraid.
Meg's new cleaning firm has been turning down some big jobs. To ensure it doesn't happen again, she needs to get her hiring done and dusted.
But I'm hoping we can be of service very soon.
Indeed can help her find great people fast.
I need Indeed.
More iconic duo than who? All right. What do we feel like tonight? Probably ought to do some black belt forms. So I don't forget them. Biceps feeling a little weird tonight. Ooh, that wasn't fun. Oh. Man, that was not nice. That just did something. I don't know if that's from holding my mouse or what, but whatever. It's all good. Alright. So, typical... Gotta see if we can do some of the Tai Chi warm-ups. Get that... I think it's the synovial fluid. Maybe that's only in one place. But try to get some of the fluid in the body, not just your blood, but all the rest of it pumping as well. Keeps everything nicely lubricated so that you can, you know, move around a little bit easier. That's also one of the things about martial arts, is that typically when you move, you don't want to be putting a whole lot of weight and motion into things because you're going to hurt something. But if you typically end up putting like a little bit of just kind of a relaxed movement, and then at the last second you snap everything, it ends up hurting yourself a lot less. And typically also imparting a lot more force. Alright, so let's see. Black belt number 1 is Shinte. That is... oh dear. Oh, I've forgotten so much of this. Alright, so we go. Sit. That was wrong. Let's try that again. From... would have gone from here to here. Whoa! In step. I've got no room is the other problem. There we go. That was the reason why I didn't step. And then next is the other black felt form. If you don't know the name of it, you don't deserve to do it. Man. Shinte was that one. Next one is Boss Side Eye. There we go. The other thing is you sometimes just need to do it. To remind yourself how to do it. Nope. That way. Chop. And then we return the side. That is a coil. Chop, punch, back fist. Return. Chop, punch, back fist. Oi. Sudo. Man, it's been a year since I was in the organization. I'm already losing it. Nope. We're here. Now we do a pierce, rip. If anybody's curious what you are ripping, notice where your hand was and where it went. It was open here. It was closed here. All right. Nope. Kick, then punch. Righto. Good times. I could probably make the cones look more like a literal eye. That would be iconic. Alright, then excuse me while I breathe hard for a bit. Alright, Math Night. Cool. Highlight the bookshelf more. Alright. Alright, so we have the hyperbola, which is shaped similarly to the parabola. However, let's see, is there a good? No, never mind. There's no good way to do it right now, but if you were to take a light source and you put a light source that has a round opening on it, so these particular ones do, They're not really recessed though. They're pretty much at the opening. You can see right there. Like that's just a light. It's super bright. The top or the tip of the light bulb is essentially right at the opening. So it doesn't get much in the way of like a round shield. Whereas, for instance, if you had a, like, obviously not glass, but if you had a lampshade, if this was upside down. If you had a lampshade sitting over the top of your lamp, that's blocking most of the light from coming out this part. And then usually there's a circular opening at the top and a circular opening at the bottom. Usually the bottom one's bigger. If you were to put that lamp next to a wall, you would be able to see half of a hyperbola. Right, the light source is emanating out from the top of your lamp. Almost. It's probably good enough. Right, and it is hitting all of the parts of the that one. It's not as good. I'll get it eventually. Right, it's going to clip against all of the parts of the top of the lampshade, and then it's going to hit the wall at different heights depending on the angle at which your bulb can then shine out of the top of the lampshade. So what's going to happen is that you're going to get something like this one here from the side, which is closest to the wall, is going to get a little bit of a shallower angle for it to then hit the wall. And then all the light that's coming out of the bulb is then hitting the, front, the wall side of the circle, and everything that's on the underside of that particular circle is just going to get blocked by the lampshade. So that's most of the light in those directions, which is horizontal and some of the upward angles, right? Those all get shaded out. But then everything that comes through the areas above that is then going to be able to shine on the wall. Typically what you get is something that looks like this until you have all the light that goes out, like all these parts, which are really, really far toward the side of the circle. The individual photons that are coming out, first of all, they have to travel further to get to that part of the lampshade. Second of all, if you picked any two places on this circle and you said let's measure the distance between these two photons that are coming out and where they're hitting on the circle and where they're going to hit on the wall, you'd look at it and be like, okay, if they're this far apart on the front side of the circle, then the photons that come out are going to hit the wall really close together. So that means that we're going to get kind of a bright spot in this area. It's going to be again, this low part of the hyperbola. But then as you get further and further out in the circle, just a slight angular difference between these two spaces on the circle, even if they're the same physical distance apart, it's going to change the angle a bit more, and the either sine or cosine values, whichever one we're using here. I feel like that's probably a cosine value. Right, because at 90 degrees in either direction, we're going to get no photons hitting the wall at all. Right, so it's a cosine function. It's going to start at 1, and then it's going to go out towards 0. Right, so this part that goes through there, you know what? Let's change that color too. Right, the same thing happens over here. So we get these things. Well, if we got parts that never end up hitting the wall, and then photons, which, again, as we start getting further and further and further out toward 90 degrees, the physical distance between where those photons hit on the circle is going to be the same, because as you sweep around, right, it's not going to change. And in fact, I think I misspoke there. The angular distance between them isn't going to change either, right? It's going to be the same number of degrees, number of radians as you go along the circle. But what's going to change is their projection along the wall. So you end up with a much larger distance between the projection points if you're close to 90 degrees than if you're close to 0 degrees. So if we, called this angle, theta equals 0 degrees, which I know everybody's going to be like, why did you do that? Right, and then theta equals 90 degrees over here, and theta equals negative 90 degrees over here. Right, these will never end up hitting the wall. Since that's a cosine function, the overall is probably going to be a tangent, right? It's probably going to be a tangent function, because as you hit either 90 or negative 90, we have an infinite distance before these photons allegedly hit the wall. So that has to be division by 0. So that's going to be a tangent function, right? Sine over cosine. In theory, yeah, sure, it could be a secant instead, I guess. But I'm not worried about that right now. So what we've got instead then is that as the photons get further and further toward 90 degrees, they end up hitting spaces which are further apart than they would be if they were at 0 degrees along the wall. So as we get further and further out toward negative 90 and positive 90 degrees, the two photons which were evenly spaced around the lampshade are now projected on the wall much further apart. And so it becomes dimmer and dimmer and dimmer as it goes. Again, not just because of that, but also because the distance drops off. As you go further and further and further away, you also end up with this other phenomenon where the intensity of light drops off as the square of the distance. So if you end up going twice as far to get to the wall, the intensity of that light is now going to be dropped to 1/4 the original intensity. So there's two different things working here. If you try to calculate one of them, right, like, oh, let's just calculate how intense is the light based on the distance that we are away, and like what's the intensity of the light in the hyperbola, then you'd end up with something that just slightly is off from what we would have kind of naturally measured. So we have those two reasons which are going to determine like how the intensity of the light is going to end up dropping off. So it's not strictly just the distance, or maybe I probably misspoke again. The distance, technically, right, it's always going to be, the intensity is always going to drop off as the square of the distance, but the distance that we hit is technically going to be determined by the plane and the distance that we are away from the wall. So, okay, it's going to be baked into it. It's like the locations that we hit on the wall, which are the distances that we are away from the light source, are going to be deterministic and going to be determined by the particular angle. Oh man. I feel like I've done this before. Back myself into a corner somewhere. Just be like, Okay, so the important point. And there's the Ko-Fi. Perfect timing, Ko-Fi. Thank you very much. You want to see this inept idiot talk more? Donate here. Okay. I'm not that bad, I promise. So what we end up having is that this is going to start going out further and further and further. But its distance is always going to end up being, or like its shape is always going to end up being blocked in by two particular lines. So, perspective-wise, this is probably a little wrong because, you know, like the salmony-colored lines there are in 2 dimensions at the light source, rather than in 2 dimensions at the wall. But anyway, if we project the center point of this over to the wall, then we end up with 2 lines as a part of the hyperbola, which end up drawing something like this. Which end up causing us to have a shape that's like this. Very interestingly, right? We end up with these lines in green, which are going off to infinity, and our hyperbola will never cross those lines. In fact, they are asymptotic. So the asymptotes are going to end up being just 2 lines, which are going to end up being the same equations as like the outside of the cones. So if we actually turned the hyperbola, right, in our picture, and we ended up driving our we ended up driving the plane straight up and down through the double cone, then we end up with like two places identical to each other and equidistant from the center point, which is not in either of these things, by the way. Which would then come from here and get closer and closer and closer to the outside curves. Again, getting closer and closer and closer to those edges forever. So, yes, they are slant asymptotes. They just have, like, the equation, which is going to be equivalent to looking at the edges of the cone. There's usually, like, an absolute value equation that you could create that is going to explain it in one. So you just say, like, you know, the absolute value of y is equal to the following. Other option, y is equal to... I feel like I want to be able to do this in one. It might be the absolute value of y is equal to an absolute value function, and so you get, like, both of them going at the same time. Right, because then it's going to be absolute value and the negative absolute value going down. I feel like that's too hard, but no, that's probably right. Anyway, it's going to do something like that. Okay. So the basic point of all this is that all conic sections follow the same pattern, which is that they have the equation ax squared plus bxy plus cy squared plus dx plus ey, nope, plus f is equal to 0. Generally speaking, right, these are going to be called, because we have a square in it, and because here we're mixing the two variables, each with a exponent of 1, if you sum up all of the exponents in all of the cases individually, they all, those three, add up to 2, right? 2x is no y's. 1x, 1y is 2 things. Hate to say it like that. And then y squared, no x's, is 2. So the maximum degree is that this is a degree 2 conic section, or degree 2 equation? Do we just call it equation? Yeah. Or we can call it second degree. If you want to get really fancy, you can call it a second degree Diophantine equation. And then pretty much everybody who's studied that knows exactly what you're talking about, and nobody else. So Diophantus was a Roman mathematician who studied mathematics kind of at the beginning of the Roman Empire, or toward the beginning of the Roman Empire, when it was kind of like, you know, the Romans and Greeks were still fighting over stuff, before the Greeks just kind of got wiped out. I should be clear about that. Before the Greek government was wiped out, the Greek Empire was wiped out, the people are still there. Right. If b is equal to 0, then your shape will be whichever shape it is, right? Right, the shape of the oh, right, okay. And A and C are not equal to 0. That's kind of important. Then the shape of no, your shape will be. Parallel to one of the coordinate axes. I don't like the way that the book worded it. That's my confusion. I shouldn't say shape either, right? This is going to be right, a line of symmetry will be parallel to one of the coordinate axes. So that covers circle. In which case it might end up being one of the coordinate axes. That's okay too. It's a line can technically be parallel to itself, sure. If it's been sent off transformed in some way, then again it's going to be parallel too. That's fine. You can just go with that. If b is not 0, we can technically find a coordinate system in which the new b2 equals 0. So there's a way to manipulate all this stuff that you could end up just changing coordinate systems. I've been learning a bit about that in tensor calc, but like that's a doctorate level course. You don't need that. I guess it might be a master's level course. And like that new coordinate system will end up with a b value of 0, so it ends up that, yeah, again, one of the lines of symmetry is going to be parallel to one of the coordinate axes of the new system, no matter what shape you get. But in our standard xy coordinates, if b is not equal to 0, then you're going to get an ellipse that's going to be like, you know, diagonal or whatever. That's fine. Might make it a little hard if you're not used to it. Okay. So for lines, right? We could, in theory, talk about points, but again, like how do you work out points on this thing? A single point is just going to be x equals a number and y equals a number. So like, how do we put that into an equation form of that form? Kind of don't. Right, because we have two equations, and now we want to simplify it to try to make only one. Well, if we end up with variables, x and y, as like separate things, or as things in one equation, then it's going to make a line, right? If we end up with like, okay, what if y just isn't there, and it's just x? Well, now you've just got x's, right? If like e is 0 and a, b, and c are all 0, right? Just take all them out. What's left? Okay, d and f. Now we can solve for x. Cool, now we've got a number that is not 0 for x, but now what could y be? Well, if it was that, it could be literally anything. Right, so we need a second equation in order to define a single point. So it doesn't really work in terms of like the conic sections equation. You just need to have two equations where one tells you where x is and one tells you where y is. In theory, you could also come up with a set of equations whose solutions are those points. Or like one equation where the solution is that one point for in some way, shape, or form, right? But I can't think of one offhand, which would be nice. And again, the only example that I'm really thinking of is where are the sides of the cone? You can make two equations, which then cross at that one point. That comes back in hyperbolas anyway. It's a long-winded way of saying that. Sorry. Basically, you can't do points as the conic section equation, as we said earlier. Like, oh, sure, a point is a conic section. Fine. I've got no problem with that. But now, how do you make it out of a single equation? You don't. You have to have two equations and tell me exactly where x and exactly where y exist, and that's it. Lines, right. So in this particular case, a, b, and c are all 0. So this is from the original, this is dx plus ey plus f is equal to 0. We've done this before. It was called ax plus by equals c. Equals c, right? That's the same thing as this. It's just shifted around a bit. Right, from Algebra 1, we get taught this all the time. ax plus by equals c. All right, cool. In this case, because we've defined what all of these coefficients are, it's just going to be dx plus ey equals f. Or no, plus f equals 0. But it's all the same stuff. For this, we do have to state that d and e cannot be both 0 at the same time. So I'm going to do something weird. Sure, that works. D and E do not intersect at 0. So as long as both of them individually are separate numbers, or they're the same number but not 0, then I don't care. You know, they can be anything you want. F can be any number we want. And again, all of our coefficients, A, B, C, D, E, F, all have to be real numbers. Don't do that to me. Come on. There we go. Sorry. Just hitting buttons all over the place, apparently. All right, so we... A, B, C, D, E, F all belong to real numbers. Doesn't matter what they are as long as they are real. If we want to get complex numbers involved, then there's a whole lot of other stuff going on. Yeah, oh, yeah, that's another way of saying it. I could also instead say D times E. No, wait, hang on. No, that proves that at least one of them has to be 0. Never mind. Right, so I was thinking in our zero product property, right? We start with the assumption that the product of these two numbers is 0. Yeah, that's true. I was trying to do like simple mathematical notation, but I don't know if that's technically, you know, correct. But again, it gets the point across. D and E cannot intersect at 0, but they can intersect anywhere else, and either of them can be 0. It's just that you can't have the intersection at 0. So here's the thing. I don't care if the product is 0. The product can be 0. That's fine, as long as only one of them is 0. So this is one of those situations where people use or rather gratuitously on the zero product property. And there you go. Yeah. People use the word or rather gratuitously on the on the definition. So a lot of times people will say, if, I don't want to use, not that one. X times y equals 0. Well, that implies that x equals 0 or y equals 0. Most people, in their mind, are replacing or with XOR. Which is the exclusive OR. Which is to say that only one of them can be 0. So again, most people just kind of do that in their mind when they see the zero product property. And I have to remind them that no, what this really means is right, this is also a possibility. It implies that x is 0 or y is 0 or both. Now, in most cases, when we start talking about like, x times x plus 1 equals 0, right, then what we've got is that x equals 0 or x plus 1 equals 0. And if you try to say or x equals x plus 1 equals 0, that's not possible, right? This one doesn't work. You're only in one variable. But the second you move to two variables, this is perfectly fine. We can do that all we want. just going to move that over there. So anyway, this is what we get for that one. Yeah. Right, x could be 0, y could be -1, and the product is 0. We could have either of them individually or both at the same time if we have the point 0, -1. Right? That satisfies that equation. But what we want here is that D and E cannot both be 0, so like their intersection can't be 0. But we can take anything else we want. Any value for D, any value for E, as long as it's not at 0 and 0. So I mean, like if we wanted to do a DE plane, right? That's the only hole. Take anything else you want in the entire fabric of space-time here. Yep. Yeah, that's also possible. Right, so D, comma E cannot equal 0, 0. Just leave it like that. Sure, why not? Okay, so we've got this dx plus ey plus f equals 0. We could put it into many different forms and all that good stuff. I'm trying to think, like, how can we naturally come up with a nicer version of it? You can't really. It's just... right, if we were to move stuff around, we get, like, ey is equal to negative dx plus minus f. And y could be equal to negative d over e times x minus f over e. Could get something that looks like this. We know what this is, right? This is your slope-intercept form, where negative d over e usually is referred to as m, which is our slope, and that b value that we typically use, lowercase b, not the same as the b that's just over there, just is going to be negative f over e from the original conic section equation, right? And this is going to be y value of y-intercept. Zero comma b. So in this particular case, yes, right? Because if e is 0, then what we have is x equals something. And so that's going to actually be a vertical line. Right? So e cannot be 0. Makes this.
So, I was thinking in this room, we'll go a bit, whoa!
Right.
You know, a sofa that really says, boom, yeah!
Okay.
And curtains that are all, yowzers, baby!
So...
We're going to get a vertical line. And in that case, again, we can go back to the beginning and say that that's going to be dx plus f is equal to 0. And then we're just solving it again. So this is going to be x is equal to negative f over d. Whoops. Just so close. Right, so we end up with x equals negative f over d, which is just the vertical line. Otherwise, our slope-intercept form, which typically is going to be y equals mx plus b, looks like that. Ew. You could. But then you're graphing a non-horizontal, non-vertical line. Right? And then like if you do x equals with a whole bunch of stuff after it, it's going to be equivalent to our y equals that we're used to. And now you just got to think like, okay, well that's slope in the opposite direction, so now it's going to be like that way instead of that way. Or no, hang on. It's not necessarily negative and positive. It has to be reflected across the line y equals x. Right, it's still going to be positive, or it's still going to be negative, whatever it was before. But now it's going to have the reciprocal value. Yeah, but again, I wouldn't be too worried about it. We don't typically do stuff like that. So then the other version of this there's going to be a function transformation version, which we say is going to look like y equals a times parentheses x minus b, nope, x minus c plus d on the outside. Right, so now our function transformation version looks like this, and to get there from here, it's a little bit harder. We have to take out your negative d over e from the beginning of that, and that becomes our a value. So y equals negative d over e times x. Those have same sign. Oh. Negative d plus d. This is going to get really ugly. There is no possible way that anybody would have to know this, but this is fun for me to think about. This is the third of the lecture, which is only for me. Right, so d over e, negative d over e is going to be removed, and that gets us the 1. The rest of it ends up leaving. It's not, though. It's not f over d. I wish. Right, so we end up with okay, I'm going to separate these first. So this is going to be negative f minus d plus d all over e like that. Negative d over e plus negative f plus d over e. Okay, so this is kind of like the easier way to solve it, or the easier way to get it. It doesn't really matter. Right, so that could be plus 1, and then we end up with plus d minus f over e on the outside. But here's the thing. There are an infinite number of solutions that work. So yours could potentially work if you just said, okay, this is going to go through 0 comma negative f over e, therefore this is what we're going to get if we like shifted a certain amount. If we were to shift it to the x-intercept, so if we shifted it over along the x-axis, right, this is just a point. Nah, I mean, this is not easy, right? This is something to at least take a minute and think about it, because, yeah, it's going to be a little weird. So if we don't want anything to be on the outside, if we assume that our D transformation, that our vertical transformation is 0, and therefore we're just sliding along, that's what I should have thought about it like that. If D is 0 and we want only C to tell us how far we're sliding it, then what we're going to get is what you said. Right? So we could get y equals negative d over e. We assume that there is no transformation, so that number right there, negative f over e, is purely having negative d over e factored from it. Then yes, right, we do end up with, you factored out d, so f over d, yes. And it's going to be a plus. So this will have a plus 0 on the outside. Maybe that's something that's beneficial to somebody, right? And then a 0 on the inside is just this one. Right? Having a 0 on the inside just gets us that equation right there. Because of course it does. That's what the point is. Right, so our function transformation can get us literally anything you want here. If we want it to be whole numbers of x shifts, then that's easy enough to do. If we want no y shift at all, that's another thing. Again, look for the x-intercept where we are. Yep, alright. No, okay. I never know what you all are getting for these. Because some will be literally 3 minutes, and some will be just 30 seconds. But it still says add break ends in 2 minutes. You know, the problem was that I had OBS overlaying over the top of my browser window. So then I couldn't see the warning that, hey, it's coming up in 5 minutes. Rawr. don't do that. Right, how do we find a relationship between these two things? So, I mean, if we want to do like really generic, we could say here that we've got hey to everybody who just came back. So I was saying here that if we want something like super generic rather than having these particular things, we could, one, find an actual equation that relates them. So here we could create another equation which defines our equation. That's probably crazy. So like this is our slope of the second one, which is d squared minus df minus 0, so that doesn't do anything, over denominator also gets a dE, so that's negative dE minus EF. It's pretty gross. I don't know that I want to do this. But this could be a way that we relate our points that we end up getting from from x1, y1. Right, so y1 is going to be equal to this nasty mess, d squared minus df over negative dE minus EF times x1 plus, and this is going to be f over d. So like our y1 could get all of this stuff instead. I'm just going to say no thank you. I don't want to do that. No. Okay, but in order to be super generic about it, this is also another way to do it. So it goes through the point x1 comma y1. And that's it. We just say, all right, good enough. Horizontal shift of 10. Okay, so you don't get to define both. That's the other thing. You can plug one in and then figure out what it does to the other one. But you're not able to say, here is one that, like, I can guarantee in this particular point, it's going to go this far this way and this far this way. It doesn't necessarily work if that's not the slope. Alright, given 5,9 is a point. Come on. No. Firefox just had a fit. Oh. Oh, crap. No, never mind. We're good. It was my tablet again. You know what? I figured it out. That is what happened to me a while ago when like everything would freeze up and then I'd have to, like, I decided, okay, I can't touch anything. I'm going to just restart my computer. This is what happened. It was that the tablet asserted control over everything, and then I was not able to touch anything on the entire desktop. Like, nothing. Alt-tab didn't work. Trying to click into stuff didn't work. Trying to use my mouse didn't work. Like, nothing at all. So I couldn't figure out what it was. It's just the tablet, like, asserting itself over everything else. So you tap escape a bunch of times. Thanks, Silver. How's it going?
You know, a sofa that really says, boom, yeah,
style and budget.
Oculus? Psh.
Oh, that is so zap.
Get it out of your head and into your home with wayfair.co.uk.
Anyway, this is good enough. Alright, if you're assuming 5, 9 is a point, and d plus f is equal to 0. Okay. So we're going to take that over here. Dx plus ey plus f is equal to 0, such that d plus f equals 0, therefore d equals negative f. And x, y equals 5, 9 is a point. Find the rest of the equation. Alright. Should be easy enough. Asterisk. So we go d times 5 plus nope. E times 9 minus d is equal to 0. Therefore, we can come over here and say that there is a relationship between d and e. Substitute like a teacher. Yeah, if possible. That's fine. Split my nose earlier. I've got like a pimple or something that grew on the inside of my nose, and then it's like a cold sore. It just keeps opening up. It's really annoying. Okay, so if we bring this over, it's going to be 4d plus 9e is equal to 0. Therefore, e is equal to negative 4/9 d. Looks like you'd have two things not wanting to break apart. Maybe. But, like I said, there's kind of a reason that this works the way it does. It's just that we have a point. We don't know what that point is, and it can be literally any point, x1, y1. The only difference is that x1 and y1 have this relationship here, which again I would not wish upon my worst enemies, to like require them to show where that is or how that relationship works. So with only knowing that our slope and the constant value are the same, I don't know. Yeah. I don't know that we necessarily have enough information. It may come down to one equation with two unknowns. And that's fine. Yes. I mean, we have it. I mean, you could solve it either way here, but either way. So if we go back, right, this is going to be dx plus negative 4/9 dy minus d is equal to 0. This will at least get us something. So it might be really ugly, but If we want to then solve, right, y is going to be equal to this is going to be a negative 9/4. Nope. D is now in the denominator. 9/4D times negative D, parentheses, x minus 1. When that D goes to the other side, it becomes a plus 1. Now we got an equation. That's good. Yeah. So, actually, in this particular case, all terms have a D, so they divide out. So y is equal to negative 9/4. There's a negative there, which makes that positive, times x minus 1. Does it? Yep. So the values of D, E, and F, like, technically are just dependent upon each other. So it just all goes away. However, we could reverse engineer it if we wanted. This could be 4y is equal to 9x minus 9, and therefore that's going to be equal to negative 9x plus 4y plus 9 is equal to 0. So, like, those are the values for D, E, and F. If they are rational, then it cleans up very nicely. Yeah, again, because D is dependent, or rather, all terms D, E, and F are dependent upon D. They're all dependent upon each other. We ended up being able to solve them and then just divide through by D. We assumed that D was not 0, so therefore we could just clean it out. I mean, I do kind of want to get through a little bit more of this, but... Alright. Oh, no, I misunderstood what you were saying before. So, if you take the original and then do that, that'll work fine. I thought what you were specifically talking about was for, like, this particular case, if we did something with it, there's no guarantee that the line itself has the slope vertical 9, horizontal 5 or 10 or whatever. I don't know. But no, it's, yeah, I misunderstood. But you said shift horizontally 10, so that's x minus 10 plus e times y vertical shift of 9 plus f equals 0. So, I mean, I can tell you already, this is only going to affect f. because we can take this back down to dx minus 10x, nope, 10d plus ey minus 9e plus f is equal to 0. So function transformations themselves of these things are almost trivial. Oh. Okay, same thing. Pick one or the other. Either way, it's just going to affect f, right? These are constants. So if you want, we could just say that this is this is the exact same dx plus ey, and now we have like an f1 equals 0. Yeah. So the point there really is that when you're doing function transformations and it was just a shift, then it's not changing the overall shape of the thing itself. So if, for instance, you said, give me something that has a horizontal compression value of 2 and a horizontal shift of 10, right? Then we get this. Now that 2 is going to affect the d. So it's going to be twice as big. The d is going to be twice as big. And then we've got the 10, which then gets multiplied to become negative 20, times d, which then goes to affect f. Right, so this is going to be 2dx, and then that would be a minus 20d, which then goes and affects the f. So that term affects f only. But then we've also got this 2 here, which is going to multiply our d. Right, so horizontal shrink, you're multiplying the horizontal shrink, or horizontal compression is my favorite way of saying it. Then that's going to multiply the d value in front of the x, and you're going to get that horizontal compression. If you want a smaller value, so if you multiply by a half or something like that, then it's going to shrink the value of the d that's out front. It's going to take the whole graph and then cause it to compress less. So it will stretch in the horizontal direction. I don't like using the same words for these two different things because people get confused about them. Okay. Oops. All right, well, we're probably not completing pre-calc tonight. That's fine. All right, so we got lines. And then as a reminder, this is going to make y minus y1 is equal to negative d over e times x minus x1, which is also going to be y minus y1 over x minus x1, which is equal to negative d over e, which again, that's the exact same thing as the slope. So our negative d over e, just again confirmation, that's going to be the slope of the line itself. Okay, then when we start talking about parabolas, right, there's certain ways that you can define them. So I ended up taking it with my class and just saying, if we wanted to, here's the way that we can build them. And it was, again, starting with function transformation and then trying to find out from the different forms. So we could start with y equals ax plus bx plus c. These are going to be like asterisk. Those are not the same values that we typically call b and c in function transformation. This is going to be the, as much as I hate the word being used, the standard form. But by whose standard precisely are we calling it the standard form? So I prefer the term generic or polynomial or expanded polynomial or whatever that is. I don't know what you mean. Oh, squared. Thank you. Yes. Now the reason why I didn't asterisk the a is because when we look at function transformation, right, we look at function transformation, and as it turns out, when we multiply all of this out, we still get an a here. We get b squared there. We get x squared minus 2cx plus c squared plus d. Turns out that this a right here is exactly the same thing as it always was, but at this point we've got this b squared here, which might affect it. Doesn't always, but it might. All right, x squared minus negative, oops, that was already there, 2ab squared cx plus ab squared c squared plus d. So generally speaking, when we have stuff in transformation form with polynomials or with parabolas specifically, I'll typically say, look, what you really want to do is you want to take this y equals a times b minus, x minus c parentheses squared plus d, and say, all right, let's get that b squared completely separate from everything else. And then we say that this is just a star x minus c plus d. It's a thing that's multiplied out front. Who cares, right? It's always just going to be a constant multiplied squared. It's always going to be a constant that's just multiplied to the rest of the stuff. So now this a star here matches this a here. So I guess we could also call that a star. But main point is this b and this c are not the same as this b and this c. Right? Really big, really important. right? Doesn't need to be so complicated. Just look at that one, right? This is going to be y equals a times the quantity x squared minus 2ac x plus a c squared. Oh no, man. I'm already multiplying stuff in. It's all good. A times x squared minus 2ac x plus ac squared plus d. So that means that now what we've got is stuff where all of this here and all of this here are just equivalent to the thing that we had up top. The negative 2ac is equivalent to b star, and the ac squared plus d is equivalent to c star from up above. The other way that I got around this was we said, well, in Algebra 1, Algebra 2, generally, we look at the transformation form and call it something slightly different. So, ta-da! Right? Y equals a times parentheses x minus h all squared plus k. So use h and k instead of a, b, c, and d. And then we don't have a problem. There's no overlap. Hey, people are allowed to make mistakes. Right, vertex form is equivalent to the transformation form. Right, we just call things a little bit different. So, whatever. It's all good. So this ends up being y equals a x squared minus 2 a h x plus a k squared plus d k. Right. So I was wrong here. Wait, hang on. That's h. H squared. Man. Right, so what does that mean? Again, we got negative 2AH is equivalent to the B star we had earlier, and AH squared plus K is equivalent to the C star that we had earlier from our generic form. So then this also allows us to say, like, okay, well, the vertex was H comma K. That's it, right? But what is it going to be in generic form? Like, okay, yes, you already know what it is, but what we want to do now is reverse engineer what are H and K in terms of B star and C star. So B star is equal to negative 2AH, therefore H is equal to B over negative 2A. That should look familiar. Negative B over 2A, comma. Right, and then K is going to be equal to C star minus A parentheses H, negative B over 2A, squared. Thank you for the follow, Lyrical. Good evening and welcome. Anybody else who's new here, my name is Obi-Wan Pez. This is Simplex Pachinko. Why do they call me Obi-Wan Pez? We may never know. I also looked a lot more like that when I was like 24. A times. This is now going to be b squared over 4a squared. And if we simplify this a little bit, work with stuff that's here, this is going to be c squared, b star technically squared, minus this a, and the one of the a's on the bottom is going to divide out, so we end up with b star squared over 4a. And then if we combine these two pieces, this is going to be a 4a over 4a times the c that was already there, minus b star squared that was already there from before. Again, should look suspiciously familiar. So there's some ways in which this is pretty nice. Again, we can back this off and just say, well, this is going to be our c minus b squared over 4a. Right, take that one, put it up there. And then if we happen to need that later, come look at that one. Right, so where are the intercepts? Right, in generic form. This is trivially easy to find one of them, right? So we set x equal to 0. So y equals c when x is equal to 0. And so we get 0, comma c for the y-intercept. Right? How does that come about in the other one, in our vertex form? Nope, not C. Let's do H. We said that we want x equals 0. So y is equal to AH squared plus k. We've seen that before. That was right up there. Ta-da! Which also is the c value that we had earlier. We know that c is equal to AH squared plus k. So the fact that we just got the y-intercept here is just showing us that, yeah, in fact, those are equivalent when x is equal to 0. So therefore, this is 0, comma AH squared plus k. Again, of course they are. We just said what that was back here. Right? How do we get the y-intercept, or x-intercepts? Well, here we need to plug in 0 is equal to ax squared plus bx plus c. That one's looking kind of hard. Over here, we say that this is going to be a times x minus h squared plus k. We need to solve for x. Well, guess what? This is an x. And just an x. It's got a square outside of that term, but that's fine. We can work with that. Because we can make this negative k over a is equal to x minus h squared. Take the square root of both sides. We get the square root of k over a, negative k over a, is equal to the square root of this thing is the absolute value of x minus h. Well, yeah, but... All right, what is all this? Well, this is a nice place to just kind of park it for a while. But if you wanted to, yeah, sure. We're going to say that this is x is equal to, h is going to move to the other side, so that's h. And then here, this is where we say that absolute value, right? Yes, there's restrictions. We'll worry about that in a minute. That absolute value is going to confer on the other side that this can be either the positive or negative root of negative k over a. And yes, absolutely, k needs to be a non-positive value if we're looking at this stuff here. Or a needs to be negative and k needs to be a non-negative value. Right, so negative k over a must be greater than 0 overall. Right, a is greater than 0, intersect k is less than 0. If we want to do this in mathematical notation, union a is less than 0, intersect k is greater than 0. And actually, we could have k is equal to 0 in either of these cases. Right, k can always be 0, potentially. In which case we just get h. So the x value of the vertex is the x value of the intercept. Right, so again, a is positive and k is not, or a is negative and k is not. We have to have it flip the sign, otherwise it's not going to work. Okay. So with this, what we're looking at now is that we've got this h and k inside of this parentheses here. And now we can decide, we can kind of decide how we want to make this work. So, let's see. Right. So, we could have a few different things. H is... hang on. So here's the thing, right? I actually prefer to show it this way first. Especially after I've shown this bit. Because, oh, wouldn't you know, we could just substitute and then manipulate stuff around to find the quadratic equation in terms of a, b, and c based on the quadratic equation from the vertex form in terms of h and k, which is so much easier. Like if you just look at it, right? Right, we know that x is going to be equal to, h was negative b over 2a, plus or minus square root of k, so it's negative parentheses, all over a. Where is k? That is it right there. Okay, c minus b squared over 4a. So here, x equals, this is negative b over 2a. We're going to not worry about that for the moment. Square root of, multiply both top and bottom. Well, okay, bring the negative in. Gets you b squared over 4a minus c all over a. Multiply both top and bottom within the root by 4a. Right, this gets us x equals negative b over 2a plus or minus square root of b squared over 4a times 4a. Right, just b squared. Minus 4ac. All over 4a squared. Great. Separate the square root top and bottom. X equals negative b over 2a plus or minus square root of 4a squared is going to be 2a. And then up top we've got the square root of b squared minus 4ac. And then bring the fraction together. X equals negative b plus or minus square root b squared minus 4ac all over 2a. Way nicer when you do it that way. Because now you don't have to prove it. You don't have to be like, well, let's do completing the square in order to figure out what this is going to get us. Guess what? We've already got it in that form, in vertex form. If you don't have it, if you only have generic form, then you might be in trouble. So anyway, that's there. All right. Then there is also an entirely different way based on conic sections to define the parabola. Right, the set of all points x comma y such that the distance between a line and oh wait, no. The distance. Okay, let me reword that. The distance from xy to a line, the directrix, and a point, the focus, is equivalent. Alright, what do I mean by that? Alright, draw a line. Anywhere. Right, now, for a regular parabola, it would be nice if it was just horizontal. So, if you want to make one that's diagonal, you're going to get b is not equal to 0. And then we run into the same stuff that we were talking about earlier. right? And then draw a... That's not what I want. And then draw a point. That's too big. Okay, so where are all of the points such that these are now equivalent to each other, or the distances between that particular point and both that focus and the directrix are going to be equivalent? Well, we could go like this and say, where am I going to get a... This is going to be ugly. Not big enough. Okay. Okay, so the distance between this point, that point there, the focus, and the directrix, no, that's not true either. Because the way we want to do this is we want to specifically talk about where the directrix, shortest distance to the directrix, is going to be respected. Right, and that's going to be the tangent value. So here we go up like this. We find the center of the circle. That is going to be equivalent to that distance there. It's the radius in both cases. Right, and there's going to be another one equivalent to this on the opposite side. Right here. Okay. God damn it. There's also going to be another point, which is going to be along here. Again, we just keep moving sideways until we find another point right there. It's going to be right there. Alright, that is not big enough, so we just keep having to get a larger version of the circle, totally circular, until we can figure out where all of these individual points are. Whoa. My mouse just jumped. Okay, and then we can make some bigger ones. I'm going to mostly just work on the right-hand side. Alright, where is that directrix? Going to have the exact same distance to the point. Alright, so now we take this point here and we go straight up till we reach the center of the circle. Ugh, not quite. Move that point. Okay, so it's here, and it is here. Something like that. And then what do we do? Well, eventually you're going to be able to connect the dots pretty easily. It's going to keep doing stuff like this. Right, so we have our focus here, our directrix here, and then our points can all be connected up on this curve. So we know that, again, the distance to the directrix as short as possible and the distance to the focus are always going to be the same. as each other, not necessarily as all of the other points. So there's only 2 points, generally speaking, that will have that exact distance, whatever it is that you're looking at. This one and the one that's opposite it on the other side of the line of symmetry. So based on stuff that we learned from, Algebra 2, Precalc, whatever, we have our line of symmetry, and then the points that are opposite sides, equidistant on either side, end up having the same properties. Okay. So if a point, generally speaking, is equidistant from the focus as well as the directrix, is there a way to come up with the equation of the parabola? Absolutely. If we have an equation of a parabola, is there a way to find the location of the focus and the directrix? The answer there is yes as well. It's a little bit harder to actually solve it, and it's been so long. How do we figure it out? What's P? Fixed point, get a line. Oh, yeah, of course they call them F and D because it's focus and directrix. Not F and D from the equation. Oi. Right. So your question earlier, Seth, about how is the transformation going to affect it is probably going to be much more helpful in this particular example. Because what's going to happen, ads are going to start in 3.5 minutes. So I'm going to try to get through some of this a little bit and then see what we can do. Generally speaking, there is going to be a point. In fact, there are 2. Such that this particular point is going to be on the same level as the focus. All right, assume vertex is going to be at 0, 0, and we can shift later. Right, so in fact, yeah, that's fine. What we're going to find is that if our point here is at 0, 0, we're going to have this particular point, which is going to have just x generic, and we'll call this distance here p. Since the focus and directrix must be equidistant from all points on the parabola, then the vertex must also be equidistant from the focus and parabola. So therefore this distance is also p. Right? This one down here is going to be 0, negative p, and then our entire line is going to be y equals negative p. The focus then is going to be at 0, comma, positive p. Okay. So we assume that all of these points are going to be equidistant, again, from the focus as from, this is a terrible drawing, definitely not to scale, must be equidistant from the focus as well as from the, oh no, from the directrix, right, not the x-axis. That's fine. Never mind. Right, so we want all points such that this is true. All right, ads are about to start. I'll be back in 3 minutes. Thanks for hanging around.
And then I was floating down a river of plump white pillows through a forest of fluffy cushions under a crystal pendant sky.
So that's the dream you had?
Yep.
And how you want to decorate the bedroom?
Yeah.
Right then. Wayfair it is.
With furniture and decor for every style and budget, Wayfair can turn your home dreams into reality.
Did I mention the light-up inflatable chair?
Get it out of your head and into your home with wayfair.co.uk.
All right. So what we're looking at here is we want all points x comma y such that right, this is true for those particular values. It's always equidistant. Okay. So the distance to the directrix is going to be p plus whatever the y value is that we're at. Distance to the focus is going to be a quadratic Pythagorean equation. Curses. So the square root of the x distance from the focus is just going to be whatever the x value is. Plus, right, x minus 0. The y distance is going to be whatever y value we are currently situated at, minus p, the location of the focus, squared. The y value of that particular thing, squared. So that's what we're always just going to get. Those things need to be equal to each other. So p plus y needs to be equal to the square root of x squared plus parentheses y minus p squared. So if we square both sides, this is p plus y parentheses squared is equal to x squared plus y minus p squared. That's going to clean up some terms rather nicely. So, y squared plus 2py plus p squared is equal to x squared plus y squared minus 2py plus p squared. Right, so y squared, p squared are going to all go away. And then we get, since we want to solve for y, we're going to move these over there. And we end up with a 4py is equal to x squared, and therefore y is equal to 1 over 4p times x squared. Okay, if we were doing this, so this is a y equals a times x squared parabola. And without loss of generality, x equals a times y squared parabola would just end up with x equals 1 over 4p y squared. Okay, this one's sideways. So x equals a times y squared is going to look like that. Whereas y equals a times x squared is going to look like that. Okay. So that's very generic. And again, that is dependent upon the distance that our focus is away from our vertex. Vertex assumed to be at 0, 0, but again, we can just shift it. Just like you were talking about earlier, Seth, we could shift it by simple, easy amounts. So, like y minus whatever d value we want to shift this, it's going to be equal to 1 over 4p times x minus c squared, whatever c value we want to shift this. Horizontal shift is C, vertical shift is D. So from here, vertical stretch is 1 over 4p. So if we want to increase the distance to the focus, that is going to decrease our A value. Yes, right, because that's going to push the focus further away. A high A value is going to also cause then our P to become very small. So the P value needs to be very, the P distance needs to be very close to the vertex in order to get a really tight parabola. Yeah, that works. Okay. Right. So again, that's just what that does here. Yes, if you want to then multiply it all out and try to figure out what this is going to do, then that's going to help us figure out what the generic form is going to look like. So 1 over 4p x squared minus 2xc, or cx, is going to make this a 1 over 2p times c, or c over 2p, I guess, times x plus c squared over 4p plus d. Right. So this is what our generic form is going to look like based on those p-values. If we want this thing to go downward, then just p needs to be negative. Our focus is going to be under the our focus is going to be under the x-axis, or underneath the vertex, really, right? Because we can be general about it. It's not even just shifted, it's all function transformation again. Alright, so the generic form is there. Okay. I feel way more confident about teaching this section, even though I've only really looked at it for, what, like an hour or two? And I mean, it helps especially that I've done all of, like, not that, but I've done all of this stuff actually in my pre-calc classes. So talking about getting the quadratic formula from a much easier standpoint, right? Starting from the vertex form, how do we get the x-intercepts? Turns out there's two of them. Here they are. And then over here, how to translate that into the generic form. Here's another thing that I didn't actually mention, but this right here, in Precalculus, we talk about the absolute value function as a distance equation. So really, this is saying that the distance between x, your location of the x-intercepts, and h, the vertex, is equal to this particular square root. So this means that the distance between your vertex and the x-intercept is going to get you two possible answers, because you have the vertex and now you have a distance away from that. So there's one on the left and one on the right. And then not only is it that particular distance, but like now we have numerical values for it. And looking at it in terms of what we'd talked about in like a much earlier section, right? Our h would be here, and then the distance would end up being square root negative k over a, and negative square root negative k over a. And so up here we get h plus square root negative k over a, and down here we get h minus square root negative k over a. And there's a point there, and there's a point there. So looking at this in terms of, again, the absolute value stuff that we would have taught in class, right? There's the exact way to find those values. Anyway, function transformation, we get now the generic form for based on focus and directrix. How far do these things need to be? Right, our C's and our D's in terms of the shifts are there in that equation. So now we get 1 over 4p times x squared is like our base equation if we don't shift the parabola. But now if we do shift the parabola, horizontally it adds 2 new terms, and vertically it just adds d. That's it. Keeping in mind, right, just shifting the thing is shifting also the focus and directrix. So shifting these particular points like this, or the point and the line both together, is not going to change the shape of the parabola. It's only by affecting the distance between the focus and the vertex that's going to mess up everything there. Hey, it's Ian Stuckey. Everybody, good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. A bunch of you are probably already here, but you never know. Viv! Well, good evening to you two. I'm doing quite well, thank you very much. Hey, Pan. Awesome. It is now 1 a.m. So yeah, a little late, but it's fine. We got to talking about some conic section type stuff. So well, first of all, we were talking about we were talking about the possible different kinds of conic sections that you get in analytic geometry. So we have the point, we have the line, which is if you were to take a cone, why is it called conic section, right? Take a cone, and in fact we need 2 inverted cones meeting at a single point. If you take a plane and stick them in between them, now you get a single point. If you lie it along the outside of the cone, you get a line which intersects with the plane. If you chop it through the middle somewhere at right angles to the right angle cone, then you end up getting a circle, which is going to slice, or you get a circle left over where you slice the cone. If you tilt that at all, a little bit, then you get an ellipse. If you tilt it such that it is exactly the same slope as the outside line, right, the shape of the cone itself, then you end up with a parabola. That's this one here. If you then go further, any further, you end up with the hyperbola, which is going to be a 2-sided shape here, depending on both the top and bottom cones. This is very fun. It's very easy to find a hyperbola around you. Just if you have a lampshade, like a lamp with a shade, that is circular at the top, put it near a wall. Turn it on. Alright, so anybody who's got that, you can find yourself some hyperbola real quick, which are the best thing ever. Maybe that's hyperbole. So here with lines, we already know how to get the lines, and then we said the general equation for conic sections looks like this: ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. So it's a second degree equation. It's Diophantine. The guy Diophantus did a lot of work with those way back when. I can't remember exactly what the years were. You can Google it. It's easy. If b is equal to 0, so we don't have an xy term, then we're going to have the line of symmetry around whatever shape you're using will be exactly parallel to either one of the coordinate axes. And if not, then we can find a different coordinate system in which it is. Alright, so we said, like, with a point, it's real hard to find the equation based on this conic section equation. In fact, you can't really. You need 2 separate equations in order to say x is this, y is this. That's just it. There isn't really a good way to state the equation. Because otherwise, again, if you have like an x and a y, then you've got at least a line. So that's an infinite number of points. That doesn't really help. But you can say that our point that we want to talk about is the intersection of an x plane and a y plane. So wherever those meet, that's not... Alright, technically you need a z plane as well. It's all good. An x line and a y line. It's good enough. If we want to then go with lines from the general conic section equation, we had 8 dx plus ey plus f is equal to 0 are the parts that are relevant to this particular thing. We also noted that d and e cannot both be 0 at the same time. I don't know how exactly you'd say that in nicer mathematical language, but like d comma e are not intersecting at 0 seemed reasonable at least, or d comma e as points are not 0, 0. Or graphically, it's an entire plane with d and e on the axes with a single hole at 0, 0. Sure. Alright, if we want to then find equations for the line, we've seen them in multiple forms. So ax plus by plus c equals 0, ax plus by equals c, or solve for y. In this particular case, it's y equals negative d over ex plus negative d over e times x minus f over e is slope-intercept form. We know that the slope is negative d over e and b is negative f over e. Cool. If e is not 0, this is going to work just fine. If it is 0, then we just have a vertical line where you get dx plus f equals 0, and then you solve that. Right? X equals negative f over d. This also led us to a couple of interesting ideas. So what happens if we do function transformation on this? Right, we end up with this thing. But the thing is that our horizontal shift could be literally anything, right? It's a linear function. If you shift something horizontally, it's also shifting it vertically to preserve the exact same line. You just shift it by, you know, some multiple of the slope, and you end up getting the same line all over again. So there's an infinite number of ways that we could state this. So I said, all right, let's just go with the generic one. It looks like this. And then our slope again is the difference in the x's divided by the difference in the y's divided by the difference in the x's. This was just some stuff that we were trying. It didn't work very well. If anybody is interested, my VODs are being placed on YouTube. So we have the @Obi-Wan-Pez gaming channel and @NSimplexPachinko6542 as our math content channel. So the dumping grounds for all of these. If you search for NSimplexPachinko, you will find the channel. You don't have to have the exact handle with all the numbers. In addition, let's see what else we got. When we were talking about parabolas as the next one, this got us a bunch of stuff. So we were talking about vertex form, transformation, which is transformation form, or the generic form, polynomial form. I really dislike the use of the word standard form, because by whose standard is this the standard form? I would argue that some people would actually say that vertex form is a much more standard form, or much more useful form. But we ran into some problems with the whole A, B, C, D thing when using the usual transformation coefficients. So we said that the usual ones that are used in like books and stuff like that are usually H and K instead of C and D for shifting. The B on the inside, the horizontal compression factor, is actually super easy to just move out and then reassign as part of a new A value. So we just call it y equals A times parentheses x minus c, c is your horizontal shift, all squared, plus d. Makes it much easier. And then this is what we get for, again, B and C based on those values, which we renamed to H and K. Found a nice little way to get the vertex, H comma K, in terms of A, B, and C. How do we get the intercepts? The y-intercept is trivial from our generic form. It takes very little work from the vertex form, but it looks a little bit uglier. And again, this verifies that C is equal to AH squared plus K, which we had back here somewhere. Up there. In order to find the x-intercepts, it was a little bit more involved. I said, let's skip the generic form for a second. We went to vertex form. It was much easier. The absolute value of something is a distance formula. And this is something that I do in my precalculus classes. The distance between two numbers that are subtracted, right, is the absolute value of their difference. So the distance between x and h, which are the locations of the x-intercepts, and h, the location of the vertex, is going to be equal to the square root of negative k over a. K being, again, the vertical position of the vertex. So our intercepts are now rendered as a distance in this case, and our intercepts are rendered as actual values in this case, which again are just dependent upon h and k, and the a value, which is always just sitting out front anyway. And we said if we wanted in terms of a, b, and c, then let's start from here, because like it's already done. We just need to fix up how it looks. When you plug all this stuff in, blah blah blah, right? Switch the signs of this stuff, multiply by 4a both top and bottom to get rid of the compound fraction. And now we've got this stuff. Oh look, the bottom is all squares. Take that out of the square root. So take the square root of 4a squared and we get 2a. Those are now common denominators. Put them at the bottom. And now we get the familiar formula. X is equal to negative b plus or minus square root b squared minus 4ac all over 2a. I did not sing Pop Goes the Weasel, I'm sorry. Not really. But then we could also define it as a set of points xy such that the distance from xy to a line, the directrix, and a point, the focus, is equivalent. So when we did that, I drew it out here using the circle tool and had just a random point and a random line drawn in. And by random, I mean I did not select them on purpose. I just kind of like dropped them in. So what do? Well, I find the center of the circle such that it will hit the directrix at a tangent point, just the one place, the shortest distance, and then hits the focus in some other angle. So what does that get us? Find the center of the circle. You got to do it over and over and over again, and it gets us this nice curve. It is also symmetric about our line of symmetry. We can assume at the very beginning, we're just going to say that the vertex is at 0, 0, and then we can do some shifting later. Don't worry about that. So whatever our distance P is here from the vertex to the focus, it has to be the same as from the vertex to the directrix straight down. And then we just repeat this for all of the other points, right? What else do we want? We want the distance to the directrix is going to be p plus y. So whatever p is here. Nope. whatever P is here, from the directrix to the x-axis, and then up a distance of y to wherever we are. Distance to the focus is going to be a distance formula. So it's a Pythagorean theorem, right? You can make a right triangle. Draw a line straight over from your point to the y-axis, and the horizontal distance is just going to be x. So x minus 0, all squared, plus y minus p all squared is going to get us, in this case, the vertical distance that we've traveled. So the vertical distance is always p from the focus to the x-axis, but then we're taking away whatever distance we have from the x-axis back up to the point we're using. So this is p, but then we're cutting out this little y piece down here. And then we just want that distance here. Once we get that, we set them equal to each other. Squared both sides, got rid of the square root and squared that. Expanded, we got rid of y squared on both sides and p squared on both sides. So it got us the basic equation of a y equals ax squared parabola is going to be y equals 1 over 4p times x squared. That p, again, is the distance between the focus and the vertex. So how far away from the actual mirror is the focus point? Interestingly enough, if you get an actual parabolic mirror, right? They have them as like makeup mirrors and like mirrors that you can see closer, like a magnified version of yourself in the mirror. You can find where the focus is by moving around with your eye until the picture gets so distorted you can't see anything. Reason being, all of the light that is coming and hitting, your image, your face, all that is going straight into the, and in fact, all the light around you as well. All of that light that is going straight into the mirror is being bounced through the focus, and not just in 2 dimensions, but also in 3. So it's going to all go through that one point. So if you can figure out where that focus is, it's where everything's distorted. You can't see anything. You could also calculate where it is based on this stuff. And then we said, what happens if you do function transformation? Okay, so if you shift by C and D, just move your mirror based on the coordinate points, then the D value is just going to shift it up. That's it. The C value, shifting horizontally, is going to affect everything else in terms of the equation based on... based on that C value, and then the either 2p or 4p in the denominator, and it's going to change the rest of the equation based on how much you're shifting it left and right.
Sky Vegas, the online casino, where we offer new players 50 free spins to use in your first 7 days, and 200 more when you deposit and spend £10 within 30 days, all with no wagering required. You love a good spin? Sky Vegas.
Okay. I've also been a terrible host. So anybody who is not already following Ian Stuckey, please do so. They have a Discord. They have the Twitch channel. We also have a central repository for everybody who joins, like, The Elements, which is our at-large, membership location, which is Penn Center's Discord, located there. And Penn Center also streams. Penn also does Legend of Zelda type stuff. A lot of randomizers lately. So it's been fun. um, What else were we doing? Right, parabolas, function transformation. Okay. An example, so the next problem that was given in the GRE book was okay. So find the focal length for y equals 1/5 x squared, and find the length of the latus rectum, which is the distance across the parabola, which goes through the focus and is parallel to the directrix. So, should be easy enough. Okay. So we're going to go through and we're going to say we want to find the focal length for that, which we know is going to, you know what, let's just make it 3/5 just for the hell of it, because I want to make things slightly harder on myself. It's not. So in this particular case, we know that the A value, 3/5, needs to be equal to 1/4 times P. P is the focal length. That's it. Right? And then we're going to multiply this across or what have you. This is going to end up being 4P is equal to 5/3. And then we didn't have to multiply the 4 across at all. This could just stay down there. So, bink. That's going to be 5/12. Right, so whatever units we're using for the focal length, it's going to be 5/12 of those units. Okay, provided that, again, the parabola matches the, provided the parabola matches that equation, y equals 3/5 x squared. Okay, so the length of the latus rectum, this, we didn't actually find it up there. That's fine. So we said here, I started talking about it and then we just moved on. So this distance here from negative x comma p to x comma p. Right, what is the length of the latus rectum? I mean, this is 2x, but but where are those, right? So we have P going up, and then it all depends on A. I mean, A is also 1 over 4P, so anyway, it is all dependent upon P. So, yep. So where are those x values? So we want to find the x value when the y value is equal to p. All right, find x when y equals 5/12 is equal to... Wait. Oh, no, 3/5. Whew. 3/5 x squared. All right. So when y equals the p-value and equals the equation. All right, we're good. Thought for a second there it was just going to cancel out and just give me 1. That'd be awesome, but no, that's not how that works. So here we have x squared is equal to, we're going to multiply by 5/3 on both sides. So that's going to get us 25/36. I mean, that's very pretty. Alright, and then that's going to be absolute value of x is equal to 5/6. So then 2x, again, this is going to be... I keep saying distance. It's length of latus rectum is going to be 5/3. Right, twice 5/6. It's going to be 5/3. All right, not too bad. All right, I think we're probably closing in on the end of this because it's just getting late. Right, we already talked really quick about circles. We know that r is the radius. We know that if you wanted to make a circle, then you're just going to get x squared plus y squared equals r squared. Right, if we wanted to draw this in just some random direction like this, then we could end up showing we have an x here, we have a y here, and we have a right angle there, we have an r there. And so here, Pythagorean theorem is just x squared plus y squared equals r squared. Makes it super easy. That's also something that I do in my trig class every semester, because that's pretty much the first step for trig. Now, equivalently, this is going to come back to what we had earlier. X squared plus, in this case, we have to have a y squared plus f it's going to be equal to 0, right? So the coefficients that are sitting out front really determine the curvature of the object that you have in front of the x squared and the y squared, and it's the curvature in each of those directions. So if you have a different number for your curvature in the x direction and your curvature in the y direction, then of course it's going to end up looking a bit different than a circle, right? We're going to get an ellipse if our curvatures are different in the two particular directions. In this case, we have a low y curvature and a high x curvature comparatively. And likewise, the other way around. So really what we need here is that basically f is equal to like a negative, I don't even, let's not even bother. Right, in order to get it to x squared plus y squared equals r squared, we can divide both sides, or yeah, no, divide everything by a, move the f to the other side there. So we end up with x squared plus y squared is equal to negative f over a, which is equal to r squared. So, again, the f up top there would have to be negative to make this work. If we're assuming that our a values up above were probably positive. F and A are going to have opposite signs yet again, just like they did for parabolas. Or rather, sorry, our K and our A had to be of opposite signs when we were looking at the vertex form. Which also makes sense, right? If our vertex gets shifted up, then in order to actually connect with the x-axis, you have to have your A value flip this thing down. If you want to still connect with your y-axis and your K value is negative, it's going to shift it down, and now you just automatically connect with the x-axis. Okay. So. A circle is going to have point A at -2, -3, and point B at 6, 1. Are the endpoints of a diameter. Okay, A.
And then I was floating down a river of plump white pillows
Where does the circle cross the y-axis?
under a crystal pendant sky.
So that's the
Yep.
and how you want to
B, where
Yeah.
right then.
does the ugh,
and decor
line tangent
Wayfair can turn your home dreams into reality.
to the circle
The light up inflatable chair.
Get it out of your head and into your home.
at point B?
.co.uk.
888 Casino is made to blow
Across the y-axis.
It's made for
Alright, that's too much for 5 minutes, but I don't know, we might be able to get a few more out of that.
48 hours valid for 3 days.
We got 3 snoozes. Might work.
£100. T's and C's apply.
Okay. So, point 1. If -2, -3, and 6, 1 are endpoints of a diameter, then their midpoint,
Something creamy, full of flavour, something a bit
Yazoo.
or the midpoint of
inspirations.
AB,
Delicious milk
is the center.
birthday cake or caramel blondie flavour. Using creative flavours inspired by your
2.
treats. The perfect pick meal, a reward for a busy day or just a little treat for
Find radius as
More taste with new Yazoo inspirations.
Try both flavours.
a Pythagorean theorem. Right? 3. Where does the circle cross the y-axis? Right, find the equation, and then the y values when x equals 0. I know how to do that with calc. How do you do it with... Okay. So again, -2, -3, and 6, 1. Midpoint. We're going to find... -2 and 6. -2 plus 6 over 2, comma, -3 plus 1 over 2. Right, find the average in the x and in the y direction. Turns out, it's going to be the same. Sorry, not as each other. That's going to be equivalent to finding the midpoint of this thing. So m is going to be, that's going to be 4 over 2 is 2, comma, this is going to be -3 plus 1 is -2 over 2 is -1. So that's also the center. Okay, so now how do you find the radius? We're going to take the center and either of the points. In this case, let's just do 6, 1 because it's still visible. So radius squared is going to be equal to 6 minus 2 squared plus 1 minus -1 squared. Okay, so now this is going to be 4 squared plus 2 squared is 16 plus 4 is 20. So r squared is 20, therefore r equals 2 root 5. Oh, right, r squared is 20. That's going to be much more useful. Right, we also know the center. So the equation is going to be x minus 2 squared plus y minus -1, so plus 1 squared, is equal to 20. Alright, y-axis is when x is equal to 0, so therefore this is y plus 1 parentheses squared is equal to 20. So take the square root of both sides. This is equal to 2 root 5, because we already did that up there, is equal to the absolute value of y plus 1. So y is going to be equal to -1 plus or minus 2 root 5, where this is going to be 0, comma, -1 plus 2... 2 root 5 and 0, comma, -1 minus 2 root 5. And we're turning this one up because you know what? Start over. This is from copyright-free music on Spotify. The Revolution by Exod and Naoni, if anybody's interested. Where does the line tangent to the circle at B cross the y-axis? Okay. We need to find the slope. Find the slope of AB, find the perpendicular line to it. That's the slope of the tangent line at AB. Right, we could do this pretty easily with calculus, because we've got the equation of the circle, but, like, meh, it's fine. This is easy enough. So, lowercase m. It's going to be equal to, this is change in y's, so 1 minus -3, famished. You're sorry. I'm sure. -2 minus 6. No. Backwards. Ugh. Students used to do that all the time. 6 minus -2. Is 1/2. So, m bar is going to be -2. -2 over 1. Math is one hell of a drug. Okay, it had to go through B, which is 6-1. Alright, we'll turn that back down. Alright, y equals -2 times x minus x1 plus y1. So y equals -2 times Yeah, you know what? I don't want to do that one. I want to do the other one, which is just going to be plus b. Negative 2x plus b. X is 6. Y is 1. Plus b. This is negative 12. Move it over. It's going to be 13 equals b. Bam. So 0, comma 13 is going to be the y-intercept of the tangent line at b. World of programming. Nice. Okay. That's it. Give it a couple of good bonks, and then we're out of here. Ooh. Uh-oh. Ooh. The hell? Uh-oh. I did not get the same numbers. Huh. X minus 2, parentheses squared, plus y plus 1, parentheses squared equals 20. Yep. Where it crosses the y-axis is when x equals 0. The hell? Oh! Idiot. Yeah, of course. It's fine. I took something away that should never have been taken away. Right, x equals 0. Not the x term is equal to 0. So this was not correct. That was not going to be that. And none of this is correct now. But good news, right? Easy fix. Alright, this is going to be root 16. So, y is equal to negative 1 plus or minus 4. Therefore, y is equal to negative 5 or positive 3. And therefore, the x-intercepts of these are, y-intercepts of these are going to be 0, comma, negative 5 and 0, comma 3. Yep. Now we circle it with an ellipse. We ellipse it. All right, everybody get your teachers. You do not circle your answers, you ellipse your answers. Most of the time. Actually, all the time. Sometimes you circle your answers. All right. We're going to get out of here before I go completely insane. It's fine. So thank you everybody for coming on over. We are going to head on over to, does anyone have math going on? Probably not. I only got 2 minutes. Come on. FizzBuzz, 52 hours? That can't be right. Must be minutes. You know what? That's looking good. Let's go over to FizzBuzz, who is currently working on, shoot, where'd it go? Programming content of all time. Bring your own parentheses. SICP chapter 3.4. Oh, channel's offline. Okay. Welp. Okay, still got a minute. Shit. We can make it's fine. It's fine. Do we have anybody doing math? No. Welp. We're going to go see Ace5, who is doing a co-working and studying stream, so we'll see how it goes. Ace5 is currently working on Outer Wilds DLC. So not today, but has been recently. Friend of Sabrina. I'll throw that in chat at some point. Anyway, I hope you all have a lovely day, a lovely couple of days. I will see you at the latest on Friday for gamey type stuff, and maybe tomorrow. We'll see how things are going. Hope you all have a wonderful day, wonderful rest of your week. My name is Obi-Wan Pez. This is N Simplex Pachinko. See y'all later.